So a little bit more about right angle trigonometry that we haven't seen yet with the circles. Draw my best triangle. Right triangle in particular. So here's my angle theta right there. And then here is my R, here is my X, here is my Y. So this triangle actually has two different angles, right? There's another angle up here on the other side I've been kind of ignoring most of the time. Let's say I'm going to call that angle alpha. What is alpha? Well, remember that inside of a triangle, the sum of the angles has to be 180 degrees or pi radians, right? So the sum of the interior angles is equal to pi radians, or 180 degrees. So if I already have a right angle there, that means inside of here, I've already accounted for pi over 2 radians. So that means the other two angles always have to share pi over 2. So that means my angle theta plus the other angle alpha have to add up to pi over 2 radians, or 90 degrees if we want to call it that way. When two angles add up to 90 degrees, they are called complementary angles. So these are complementary angles. And again, what does it mean to be a complementary angle? It means they add up to 90 degrees or pi over 2 radians. Okay? And again, radians are more important than degrees in trigonometry, so we're going to focus on that. So if I know what theta is, then I can find alpha. Right? So if somebody says, hey, your angle theta is equal to pi over 6, and I want to know what alpha is, I know that if I take theta at pi over 6 and add it to alpha, the result has to be pi over 2. So I can just subtract the pi over 6 over. So pi over 2 minus pi over 6. Common denominator would be 6. I'm going to multiply top and bottom by 3. So 3 pi minus 1 pi is going to be 2 pi over 6, which reduces, top and bottom divides by 2, so that's pi over 3. So that's the complementary angle to pi over 6. Right? So I've just discovered that pi over 6 plus pi over 3 add up. Oops, I already got my add to equal pi over 2. In general, that's always going to be true. That other angle alpha is always going to be pi over 2 minus theta. Okay, so that's important. So we have this complementary angle relationship inside of a triangle. We often look at this lower angle in our right triangle, but our triangle could have lots of different orientations. So sometimes the other one is important to look at also. If I focus on this triangle a little bit more, where I have the angle theta and alpha, let's just look at some things there. I know if I just think about theta for a second, the cosine of theta is going to be equal to this x value divided by the radius. Now, what if I switch to the other angle? What happens there? Okay, well, if I switch instead to t and I looked at, hey, what is the cosine, or not t, alpha? If I switch to alpha, what's going on? Well, from alpha's perspective, I'm talking about the cosine. Turns out I want this y instead of the x. So a way to think about that is from theta here, the x value is next to it. That's called adjacent. So x is adjacent to theta. The y, on the other hand, is across from or opposite. right? So that's a different perspective. So another way to think about cosine is not necessarily the x value, but I want whatever leg is adjacent to my angle. So now if I think about alpha, what leg, right, not hypotenuse, what leg is adjacent to alpha? Well, x is opposite alpha. That's not what I want. I want the one that's next to it, which should be y. So when I switch my perspective to the other angle, things get flipped. So cosine of alpha in this case would have to be y over r, because y is the adjacent side to that angle. So with right angle trigonometry, we think more about adjacent and opposite sides, and then r is my hypotenuse. Talk about the sine for a second. If I look at the sine of theta, well, sine is in my standard position here down on the bottom, and so I want to take the y value divided by the radius. Why? Because the y is opposite, so that's another way to think about it. Sine wants the opposite value over the hypotenuse. And then I just need a tiny bit more room here. Let's see if I can slide this stuff up. That's going to mess up some things, but oh well. I'm just going to do that and then move that back. Oop. Just want you, please. There we go. And you. All right, so next thing I want to take a look at is the sine of the other angle, that complementary angle alpha. And thinking about the idea of opposite alpha is x. So for the sine in that case, I want the x because it is opposite that angle alpha. So right angle trigonometry, instead of thinking about x and y, what's more important is we think about opposite and adjacent legs compared to the angle that we're looking at. Now, one thing to notice once we do that is that here I have this cosine of the angle theta is x over r, but the sine of the other angle is also x over r. So let's look at that relationship for a second. So I'll redraw my triangle here and just focus on that part. So I have my angle theta here, and I have my angle alpha over here. And I'm going to label these a little bit different now. I'm going to label this one as the hypotenuse. I'm going to label, actually, no, I'm going to keep it the same way it was. Take that back. So this right here is going to be my radius. There's my right angle. That's going to be x, and that I'm going to leave that as y. So what did I just find there? I found that the cosine is what I was focusing on of theta first. Oops, wrong way. The cosine of theta was equal to x over r. But when I changed my perspective to alpha, that other complementary angle up there, x over r ended up being the sine of alpha. Other thing I noted before is that those two angles, alpha and theta, have to add up to 90 degrees or pi over 2 radians. So that means alpha has to equal pi over 2 minus theta. So what I'm going to do is I'm just going to make that replacement. I'm going to say, okay, this alpha, oops, I want a highlighter. This alpha right here is that alpha right there, and it is equal to pi over 2 minus theta, so I can just replace it up there. So now I get this new equation that says the cosine of theta is equal to the sine of the complementary angle, and the complementary angle is always pi over 2 minus theta that I started with. And this right here is called the cofunction identity. that when we switch our perspective to the other angle, sine and cosine switch places. So instead of looking through this angle right here for opposite and adjacent, if I change my perspective and look through that angle as my lens, then sine and cosine switch places, which is kind of neat. Now, if you look back at my notes previously here, it turns out we had a similar thing happen over here. So I can switch this relationship so it goes the other way too. The sine of theta is equal to the cosine of pi over 2 minus theta. And really, graphically, all this means is we're just looking at the other angle in the triangle. And if you do that, sines and cosines switch because opposite and adjacent switch. So one more view on this. So again, we have a couple of new identities we're going to add to our page of identities, these cofunction identities there. Oh, not ready for that one, almost. So I'm just going to view the triangle again. Angles are out this time just to be a little more exciting. All right, so again, right angle, classic kind of trigonometry. From the perspective of theta, this angle right here is adjacent next to, and this angle right here is opposite across from. And this side right here, instead of my radius, because I'm not in a circle, is my hypotenuse. And with those new perspectives, I just get a different way to write sine, cosine, tangent, and the other ones. I'm just going to do the top three. The sine of theta is equal to the whatever the length of the opposite side is, divided by the hypotenuse. Cosine is viewed as the adjacent, which we used to call x, and more often I still will, but sometimes this is a useful perspective, divided by the length of the hypotenuse. And tangent of theta, we used to call y over x, now we're just going to call it opposite over adjacent. So slightly different set of language, same ideas as before. The real new thing here is this idea of this complementary angle, where we have this interesting relationship between the sine and the cosine, pi over 2 radians or 90 degrees. But again, radians is more important than degrees. But radians is all over the world, so we still have to know it too.